Hello and welcome to the supplement to today's lecture. This is actually catching up from lecture 4, so you can join me on page 2 of your lecture 4 notes. I'm just going to review what we already did go over in lecture 4 on proton NMR analysis. And here I have, we're doing it on paper, and by that I mean you're not actually going to be making your own NMR sample or testing your own sample. You just are given the spectrum. And what we want to find out is how many different types of hydrogens are there? How many hydrogens are there in the molecule total? What's the relative ratio of those hydrogens? And that'll tell us how many signals or how many protons each signal is worth. And then finally, the electronic environment here is going to tell us what atoms or functional groups are nearby based on the chemical shift or the x-axis, this guy here. What we did in our 4th lecture is we talked about the symmetry in both of these molecules. So the one over here on the left, this is Benzhydrol. This was the starting material for the experiment 3 reaction. And over here is benzophenone. We talked about how there's symmetry in benzophenone through the molecule like this. So that's why we identified these two hydrogens as what we called A, or A prime rather. We then have the plane of symmetry over here, so we can see that these two are both Bs, but because of the plane of symmetry that we have through the molecule this way, because it's a benzene ring here, we also have a proton B down here and here as well, and that's why we came up with a total of 4 hydrogens for signal B, or I wanted to call it B prime, just so it was a little bit different from Benzhydrols. Finally, we have a third signal in Benzhydrol. We have plane of symmetry within the ring itself. So there's signal C, another signal C, and yet another. So we'll keep this in mind for later because it's going to help us with our calculations that C are the hydrogens, the C's, or the C primes, are the hydrogens that are ortho to the ketone. Signal B's are the ones that are meta to the ketone, and signal A's are the ones that are para to that ketone. So we talked about that in the 4th lecture, not quite that extensively, but just saying that there's 3 different protons in benzophenone. I wanted to go over just briefly without actually adding anything. I might just highlight a few things of what we actually went through, like the order of operations that we went through in order to assign all of the signals. Here's what we're actually trying to do. We're trying to make some sense of the spectra down here. So we're trying to assign each and every one of those signals to a set of protons on Benzhydrol. So which one is A, which one's B, which one's C, which one's D, which one's E. And we identified first by general groups. So here's where I'm at. We identified that these guys were all in the aromatic region. We wanted to get a little more specific than that, even though we could at that point just identify these protons right here as signals A through C, but that's not quite exact enough. So what we did is we went to table 22.4 of, it's a handout and it's also available online. I'll pull it up for you here. Right, so first here is the table where we got that 6.5 to 9 value for the aromatic compounds. And if we go to the next page, this is table 22.4. You can see we do have this additive parameter table. We had a base value of 7.36 parts per million up on the top. And then we identified that the group was closest to the second one, the CH32, and to the ortho one, we subtracted 0.14. To the meta one, we subtracted 0.08, and to the para one, we subtracted 0.2. And that's what this was all about. Hold on one second. Yeah, there we go. Okay, so that's how we got these values. These were the expected chemical shifts for signals A, B, and C. If we take a look at this zoomed in region, so we're looking here at the zoomed in region, I'm going to clean this up. It does say there are 3 signals, but I kind of want to do this again very quickly. There are 3 individual signals. This is one signal that is overlapping with this other signal that is very close to, but not quite overlapping this third signal. Those are the three, and we could identify them in order based on the chemical shifts that are given. You can see that signal B has the highest chemical shift, so this is signal B. Signal C has the second highest chemical shift right there, and signal A is right here, right? So the other thing that's helpful with that is you can see that A is a 2-hydrogen signal, so it's smaller, and B and C are both 4-hydrogen signals, so those are bigger. We then identified the remaining 2 peaks that were left. This is right here. This is signal E. It's in that range between, I'm sorry, not exactly in the range, but it's close to the range of the alcohol. So we identified that signal E was in 2 different ranges, one between 3.2 and 5.3, but it was also benzylic. We used a different table. This is table 22.3. Okay, so here's this table. We had the base value for the methine, that's the 1.5. We went down and we found that AR group and we added 1.4 to 1.5, but since there were 2 groups, we added that twice. And then if you scroll down a little bit more, you can see the OH group there, pretty close to the bottom, put it right there. So we add another 2.3 because that's even more deshielding. That's the words, but this is the actual outcome of that. So here's 2 times 1.4 because we had the aromatic group, and then we add 2.3 with the OH group. Each group is deshielding, so the expected chemical shift, was outside of that alcohol range. It's about 6.6, so it's not quite exactly right. Down here, it's pretty close. It shows up at about 5.8 parts per million. And I'm just using the x-axis here to estimate that 5.8. You'll estimate the chemical shifts for the rest of them. This is about 7.4. This one here, whatever numbers there, like 7.6 or something. And then this guy, the center of it, is right there at about 7.3. The last one is the OH signal is very broad, so that's what helps you determine that it is the OH proton or signal D. And we identify that by its main group. Where'd you go? There you are. So alcohols show up anywhere between 0.5 and 5. So that was the overall outcome and our actual objective in terms of assigning the spectrum, each signal in the spectrum, to the molecule. With that, we would go ahead and fill in the rest of this stuff. It's just really just a summary of what we have above. Signal A is a 2-hydrogen signal. We expected it to show up at 7.16. It actually showed up at about 7.3. Signal B, the 4-hydrogen signal. We expected it at 7.28. It actually showed up at 7.4. Signal C, 4 hydrogens, we expected it at 7.22. It actually showed up at about 7.36 or so. Sure, I'll just call it 7.35 because it's a little easier to compare. So it's not the number, it's the relative order. You can see that B is the most deshielded of all. We then have signal D, which is a 1-hydrogen signal, right? So that's signal D, the one right next to the alcohol there. Shows up anywhere between 0.5 and 5. Actually showed up at 2.2-ish. Last signal was signal E. We were expecting it at 6.6 was the calculation we did, and we observe it at 5.8. Okay, so this one I do for you. I help you guys out. I hope you find it useful. You will be doing these on your own in the lab practical, so just please keep that in mind as you go through and practice more NMR stuff. So now the real thing that we haven't covered yet is the chemical shifts, expected chemical shifts for benzophenone. We're going to go through each one. They are all signals A through C are in the aromatic region. So the general chemical shift range is 6.5 to 9. We want to get more specific than that. So we'll have chemical shift values more specifically for A through C. we'll go back to our correlation table, and we see that our base value for each of them is going to be 7.36. So depending on the proximity or just the relative position of each group to the tables or to the substituent, we're going to have shielding or de-shielding effects. And one thing before I switch back over to the table that I want you to keep in mind is that this is going to be a really nice, strong electron withdrawing group, which means it's going to be de-shielding or pulling electrons away from each of those protons, some more than others. You will see here in this table that the effects are felt more strongly in the ortho and para position, meaning those numbers are higher. You're going to just like take a look for a second and see that the numbers in the ortho and para columns generally are higher if you look at any one row, and that the values in the meta position are very small, generally speaking, and some are so small that it's like not even worth it to compare the effects of having a position or a group in the meta position. But we're going to scroll down, we're going to find our closest group, and the group is defined by what atom is immediately attached, and we have a carbonyl that's directly attached, and on the other side of that carbonyl, which is a ketone, we have an aromatic group. So we're looking for the C double bond oxygen with an aromatic group. We have the row that we're looking for goes 0.45 for ortho, 0.12 for meta, and 0.23 for para. See if I can remember that. I'm actually going to switch these guys around because I don't want this to be confusing, but signal C is the ortho one and signal A is the para one. So let's keep that straight. So this guy's para, this one's meta, and this one's ortho, and I've already forgotten the numbers. It goes 4, 5, 1, 2, 2, 3. Yeah, I can remember that. Okay, so these are the numbers that we're adding. They are positive values in the table, so we're adding. You may have noticed that some of them were negative values. So if they're positive values, that means those are all de-shielding groups or groups that pull electrons away from those protons. You can see a much bigger effect is felt in ortho and para, and a very small effect in meta. So there are the expected values, and I think you guys needed to watch me do my addition, but hopefully there's no mistakes there. But we can see that the most de-shielded, or the one with the highest chemical shift, the most de-shielded signal is signal C. The one that has the lowest chemical shift is the least de-shielded. Yes, that is the way that we do it. It's a double negative, but that's just the way we talk about it. The least de-shielded is going to be signal B. All right, so you may notice that there is no integration provided here. You just have to estimate what each signal is worth. You notice there's two big signals, so here's your two bigger signals, and then your other small signal. So even from that, you could just say, well, the smaller signal must be worth less protons. So that alone could be enough to tell you that this is going to be signal A. Okay, that also fits because signal A should be in the middle of the other two, right? It goes C is the most de-shielded, B is the least de-shielded, so A is right there in the middle. We were expecting it at 7.59. We actually see it at 7.6, so really not that big of a difference. So that's signal A. Signal C should be the most de-shielded. And that works out for us. We see that it does in fact show up at 7.8, which is pretty much right where we're expecting it, so hooray. We then lastly have the least de-shielded signal, and that was signal B. This is forgot to add this, but this was the 4 hydrogen signal, as was signal C, and then the smaller one was signal A for 2 hydrogens. This is, we were expecting it at 7.59. It shows up at 7.5, okay, ish. So we can see the relative relationship between each of those, and I hope you find that very useful. You're welcome to go through, or actually you're required for your report to go through and fill in all of that information into this table down here where you add in the integration, the number of hydrogens, the expected chemical shift is what we did up there at the top, and then the observed chemical shifts are just right here along the x-axis. Okay, so that's what you need to know for your report. If you're curious to know a little bit more about peak shape, I'm going to continue on with this discussion, and I hope that some of you continue and stay. All right, so I'm just going to clean up this page a little bit, clear out some stuff, and talk about some different things. So here's the cleaned up version with a question that we're going to answer together. Why does this electron withdrawing group affect the ortho and the para position, but not so much the meta position, right? Why doesn't it go, oh, that this signal C is the most de-shielded, and then signal B, and then signal A? The short answer for that is actually resonance, right? So that's the short answer. So we can draw, or we're going to draw, two resonance structures that explain this de-shielding effect. And in the context of this, we're also going to remind ourselves of what it means to be de-shielded. One resonance structure we can draw that demonstrates the electron withdrawing effect is to just pull those lone pair, or pull the pi electrons out of the ring and into that electron withdrawing group. That's why it or how it withdraws electrons. Okay, so what we end up with, double bond here, this ring here is all the same. These electrons are now up there. These two pi bonds have not moved. So the new stuff, the new thing that I'll highlight is that we have a positive charge in the ortho position. Right? If we have a positive charge in the ortho position, that is what we mean by de-shielded. We have pulled electrons away from that positive charge. There are no electrons, and in theory, there are no electrons around the positive charge. And remember, we're referring to the hydrogen attached to that carbon. That has taken away its electron shield. By electron shield, I mean we're talking about the nucleus of the proton, so that's the hydrogen's nucleus. And when electrons are around it, doesn't have to be this many, but just the idea, this would be the electron shield. But if you took away those electrons by, for example, resonance, making a positive charge there, that is what we call de-shielded. So that is explaining why we see it in the ortho position. But now we would expect, okay, well, now it should move over into the meta position, right? Well, clean that up, clean you up, all right? Let's try to move these electrons over. What happens now in our next resonance structure is that we have, let's get my single bond structure here. I'll just draw this as a pH group. I'll draw all the stuff that hasn't changed first, and then I'll draw the stuff that has changed. We've moved this double bond over and up. We've skipped over the meta position. So you cannot draw a reasonable resonance structure where the positive charge is in the meta position. So here we have the positive charge in para, and that is de-shielded as well. It's not going to be as de-shielded as the ortho position because it's a little bit farther away, but that's why we have stronger electron withdrawing effects or stronger de-shielding effects in the ortho and para position, and the meta experiences very little de-shielding. Okay, so that answers that question. That's why electron withdrawing groups, and we'll see this too with electron donating groups, effects in aromatic rings are felt more strongly in the ortho and para position and not in the meta. And that's proven with this table. So again, you can take a look, even when the values are negative there at the bottom, you can see that the magnitude of those numbers is much larger in the ortho and para position and pretty darn small there in the meta. And that's why, resonance. Last thing to point out is the splitting in each of these peaks. So let me clean some stuff up. What I want to focus on is the actual shape of each of these peaks. So each one is a signal. So like we did before, that's a signal, that's a signal, and that's a signal. And we can talk about where those signals are centered. A new topic that we'll really get into in experiment 5, but I think some of you might be interested in, is the actual peak shape, or what we call the splitting of those signals. This is caused by something called by proton to proton coupling. Now for right now, I'm not going to explain the phenomenon of how or what the coupling actually is. I'm just going to give a brief explanation of why, of which particular shape it has taken. So there's two main shapes that you see here. In signal C, it's split into two main peaks called a doublet. Now, yes, we definitely do see those two peaks split into other little things if you look even more closely, but we're just going to pretend that it's like a clean doublet, because that's as much as we need to know for right now. So a doublet means the one signal is split into those two peaks. We also have both of these guys over here, which are both triplets. And yes, they are split into like smaller signals between and beyond that, but the triplets look to make it like a little cleaner or something like that. Those are both triplets. And that's all dictated by the n+1 rule, where the n is the number of neighboring protons. This is where it's going to be useful to look back at the structure. We've already done the assignment, so now we just need to get an explanation for it. Get rid of you too. Signal C is right next to signal B. Those two affect each other. We only look one proton at a time, meaning I'm not looking at all of these C's and how they're related to all the B's. I'm just looking at one B at a time. So from that, we would say that C has one neighbor, and that neighbor is B. Now we can confirm that because we know that C is split into two signals. So if we were to try and solve for the n+1 rule, because 2 is the doublet, right? So that's what we mean by this is the multiplicity, or how many signals it's split into. So in order for that to be true, that means n must be 1. And that one neighbor is signal B, right? The one hydrogen that was assigned to signal B. So that's why C is split into a doublet. We see that signals A and C are split into triplets. So, oops, sorry. Those A and B, apologies. A and B are both split into triplets. So what we're looking at here, look at signal A first. Signal A is right next to this B, but there's a B on the other side as well. So it has two neighboring protons. Then your N is 2. So n+1 is 3, and that's how we get the triplet. The same can be said for signal B. B is coupled to signal C on one side and signal A on the other side. So they don't have to be equivalent protons. So signal, I already put stuff in the wrong place, but it's the same, it'd be the same calculation. So signal B and signal A have an n equals 2, so n+1 equals 3, and that's how we end up with a triplet. Now, clearly there's more to it of why these signals are actually split in the first place, but I like to give at least a little bit of an introduction so you can see, or at least be able to predict what the peak shape would be like. All right, so that was a second 10-minute portion, 20 minutes total. I hope you enjoyed the second half and that this was helpful for your pre-lab. Thank you very, very much for your attention, for your time. Have a wonderful weekend or week and lab and all that good stuff. All right, bye-bye.